Okay, picking up where we left off, here we are passing a D to foo here taking a B. Foo calls a member of B called the vfunc. Call the vfunc calls a function that we have replaced with our own function, and we try to print out our data. And I'm still not 100% sure how it ends up with this address because, anyway, but it's definitely not the right number. Now, what I'm going to do here is change this to a pointer instead, called PB, and call the pointer, call from the pointer, and pass the address of D into foo here. Now, this address of D should not modify the value, should not cause it, but this shouldn't do anything other than reinterpret cast, according to all our experiments before. That those weirdo things that happened happened because we had like side-by-side derivation, but for regular single level derivation, that's a reinterpret cast. I'll do both just in case. I'm going to run this first and show you that I got a 0 there. Now that could be an accident. 0 does occur, so I'm going to make this very specific. Let me make it D for derived. Okay. Make sure we get that value exactly. And we do. So now, this here, PB, is in fact a D, like it or not. And I'm going to step in here, and then to here, and I should have put this on separate line, so I don't have to do this step. I'll wait till this pointer shows up. Okay, there I am. There's my value. There's base. Of course, the base class could also have data. So let's give the base class some private data. Okay, and let's initialize that to something we'll recognize. P for base, and let's let his function do the same thing. Print it out. Okay. So there are a couple things to experiment with at this point. First, A, is I'm going to interfere in any way with our access to our own data. Well, and the answer to that question is no. And if we like, unfortunately, we don't have access to bases I, but we could, we can't access that, and we can't access that. What we could have done is saved off the previous value of this, but I don't want to do that. Maybe I can move this up to protect it, just for now. Doesn't matter, really. I just want to be able to call it and make sure that this hasn't gotten lost, that everything's still intact. So in our do the dance thing, certainly derived I is equal to that, and base I we should be able to specify this just as I've written here. Oh, I can't. It's still private, but I can call that function now. Okay, this way. Leave that as it was. And call this function, which I now have access to. It is protected. Oh, by the way, this type def didn't need to be public, so I didn't need to do that wacky public-private thing that I had. This just only needs to be used by derived classes, so there's no necessity for public access to this type def, which I can try to hide away. Okay. Now what's going to happen here is we're going to get two lines of printout. And let's see, we should get B's and D's. We do, but it's not very clean looking, is it? How about character return? I'd like to put the function name first. Maybe I can change this to printf. How about that? So there's no character return, because I'd like to put that first. Print func, and then print this out with a character return. Maybe a character. No, we'll try it like this first. Let's see how this looks. It's a little better. Oh, we definitely want a character return after this. So it was fine as it was. But anyway, this is the same. Alright. So derives gets his D and base gets his B's. Okay, fine. I could, if I wanted to, make them look even more similar. Like that. So what that means then is nothing got lost in this passing of a pointer, and the same should be true if this is a reference. So now, with no syntax change from before, other than the fact that this is a reference. It could be constant too. Those functions are constant. This should also be one call in which nothing gets lost. Because remember, internally, a reference is treated as exactly as if it were a pointer. Now we've got essentially a virtual function called call vfunc. All right. And if we wanted to add more to this, okay, what we could do, perhaps, instead of just having one of these things, we could have a table of them. Let's say we got two virtual functions, and we could provide an index here, maybe. U, I guess, for unsigned. Okay, so called the youth virtual function. Now we've got funcs. It's called funcs now. And I have a value for my zeroth one called vfunc, wherever it went. I actually prefer to make this, put this back to its private location. I'm not going to call back down to it again. And I'd like to make another one. vfunc1, right? And I'll set that to the second element. I want to make sure this has got all the entries are at least valid. For a B, D has no obligation to fill in this table, but I certainly do. I gotta make sure that I get something. I could make them both the same, but I prefer two different functions, 0 and 1, both of that type. Okay, and now I got a function where I can select one or the other. Now in derived, zeroth one I could set to this as I have already, and I could let the other one just remain as it was, as it is, whatever the default is. I'm not allowed. However, I could certainly call something through this table, right? So why don't well, that would end up calling myself. So there's nothing I can do after I've overwritten it. I could make my own table and save off the previous value, and that's probably what the compiler does in certain instances. But we'll get to that sort of thing later. Let's just have a look. That does not take 0 arguments. That's true. So we'll try calling both. I'm not doing any validation on the parameters. Let's see what happens. Okay. So calling, as expected, calling the zeroth function ended up in the virtual dance, where I was equal to these, and calling the first function put us in the base classes vfunc1. Again, I could create my own func1 if I wanted to override it, or I could do it like this. I could make my function the first element in the list. So now it's reversed. Okay. Now doing this, the way we've done it is something like, I don't know if you have seen or recall, but we had this problem when we were doing the assembler bit, where we had a bunch of functions to do with strings, and they all relied on this terminating character. And the problem was that that code was what I call non-relocatable. That is, if we move the code, we could move the code, sure, but the data, which was at a position relative to the code, would not move along with the code. Now we've sort of got that problem, or had that problem in reverse. Whereas if we move the structure, right, moving in this case by copying and sending to another function, the code, the overriding code, what we're doing here is overriding functions in here, didn't follow the data. And that's because this always and still does resolve it to exactly this. Right? It's going to, well, it's a dot. It's calling b : call b func 0. Right? But now, since we've turned that code into a piece of data, call v func, even though that's at some fixed address in memory, what it actually resolves, the function call that it resolves to, is a piece of data that moves with the structure. So if I copy the structure, that whatever property, that new functional property that this base class has acquired through having been inherited from, moves along with it. So we don't lose that new property that we've added to it. And that's the basis of virtual functions. I'm going to pause for a second here, because there's another set, the second set of experiments that I have prepared before, and I want to just find them. Okay. This is sort of the situation I wanted to invent, where our foo here returns an object of the type of the base class, and instead of now I've taken this v func, and in fact this can be private now. All of this, except for this bit, this can be private. Except you can't see that. I have to do the public, private, public. Doesn't matter. Anyway, as far as the outside world is concerned, there are two functions, 0 and 1. Okay. Now I'm going to call these virtual functions, even though they're not using a special keyword. Okay. Because they're using this table of functions that I've invented. Now, for a derived class, by the way, so the actual implementations of these functions has been moved over to here. Okay, these are the virtual function implementations. This is the declarations, and something to call through the pointer. Now, so initially these are set to the virtual function, the actual functions that are members of the class, like this. For a derived class, if I want to derive from base, and I want to override one of those functions, one or the other or both, all I need to do, of course, is just set new values in the table. Now, the way a compiler might do this would be, I would declare something of the same name, right? Even though that doesn't, in our case, that doesn't do anything, right? Call v_0. That's the implementation we want anyway. But a compiler might say, okay, therefore overwrite this value, and ignore this, right? That could be a one way of implementing it. If I give it the same name, it'll go to the table, fill it in with the new, put a V in front of here, and fill it in, and put the implementation somewhere else. As it is, I don't need to say anything. I can fix it up in my constructor. Now this foo returns something of type base, which has two exposed functions. And if I call them, I get my base versions and base data. However, if it returns something derived from base, I don't have to change anything here. And a different implementation gets called. So that is, as far as from the point of view of this function, main, if I want to change the behavior of main, whatever it does with this foo object, I don't need to change any code in here, right? All I need to do is send back a different type of object that has the same interface, and this has to have the same interface because it's derived from base. In fact, it doesn't add anything further to base. All it does is override those functions, and that is essentially the kind of the goal of one of the goals of virtual functions is to be able to declare a type of interface class like this base here and allow through the process of inheritance overriding certain properties or methods of that base in such a way that that overriding is transparent to a function that is using this interface. This thing only knows about this interface. D here could be in a totally different file. I don't have to know about D. How can I can declare this and put it somewhere else. Put it down here. And put the definition of the derived out of my view. All of it. Let me get there. And this is something that happens quite often, especially for industrial type code, where a function is handed a pointer to an interface only, and then it uses that interface without having to know what it is, what the actual implementation details are. Here the implementation is different or varying depending on the return, whatever is returned from foo, this doesn't know anything about D. It only knows about B, base, I should say. An example of this would be like, say you're making you're writing the code for a candy machine or something. You know, one of those candy machine dispensers where you put in some money, push a few buttons, and out comes your Mars bar and change or something. Now, for a device like that, okay, there are various devices attached to it. One of them, for instance, would be the thing that gives the change out, the coin dispenser. Okay, now there are probably hundreds, maybe thousands of different varieties of that particular type of device. But if you're just writing the code that tries to figure out which item to dispense and how much change to give and so on, the details of how that particular device works have nothing to do with the code that you're writing. All you want is an interface to something that dispenses coins. So you would have like coin dispenser, you know, get coin dispenser. Right, and then in your logic, your function might do the dispenser equals that initially, and then at some point you're going to go dispense coin, dispense 12 cents, something like that, right? Now, the implementation of this function is of no concern to you. It has got nothing to do with your logic. And somebody who designed the physical hardware to do the dispensing and everything would have in their implementation here all kinds of assembler code, in through this port, send this signal and wait for an acknowledgement from the device and so on and so forth, which has nothing to do with what you're doing. You want all that implementation detail hidden inside the coin dispenser object, which implements an interface, a coin dispenser interface. And that's exactly the sort of code that I've written, I've had to write when I worked for different companies. One in particular, anyway, where we used, it was a point of sale type device we were writing, and there were coin acceptors and dispensers, bills and credit card things, and all these various devices, and they all had standard interfaces. And the way we got around this part of actually retrieving a pointer to the interface and then specifying that was through the use of DLLs. In the registry, registry is where you have various settings and things. You know what I'm saying? Somewhere in the registry, I don't know, there would be some setting somewhere. Let's say this was coin dispenser. I know I can write here. This is my own key. And in here there would be a string value, interface file. I don't know whatever we called it, something like that. and then it'll give a specific one, like it'll be what are some of those companies called? I don't know. Let's say it's the NEC 2001. I don't know, because that was the particular coin dispenser device that particular cash register or whatever. We call them robots, but the particular robot was using this particular type of coin dispenser, and inside these DLLs would be a class definition, a class which would inherit from the coin dispenser interface, and it had every one of them would have a standard one single function that would be an export, just as these are DLL exports, right? And you would load the DLL, load whatever DLL you found in the registry, find that function, call that function, and it would return you a pointer, a new, use it through the new, using not malloc but new, a new object of the type desired, and then you would just use it as you would any other object. So adding different devices was simply a matter of somebody has to sit down and write down an interface class for that object and create the DLL, and then that ships with the hardware. If the hardware changes, you go in the registry and you change the value for the implementation. This is the implementation, and the interface is standardized. And so that's an abstraction layer. That's normalized behavior through these virtual style functions. Now these aren't real virtual functions. This is not happening automatically, right? For one thing, we're limited at this point to only one particular type of function, right? It has to be void, const, and returning nothing. So what they've done in C++ to get around that, well, not only get around that, but just to put the solution, to put the answer to bed and not have to worry about it ever again, was to invent a new keyword. So I guess I can get rid of all this now. Let me check my time. Right, I'm out of time, but there's a new keyword that will go in the front of these functions called virtual. There we go. Like this, okay, virtual func. Now the type arguments could be anything, whether it's constant or not, return value and everything are automatically taken into account. Similar to this, there's a table. A table is created with pointers to the functions that are declared this way. And in order to override one of these functions, a derived class simply declares a function with exactly the same name, same return value, same arguments, same modifiers, and then that function's version will be placed into the table. Okay? And I'll show you next time. I'll show you that happening. There are some differences. For one thing, the mistake that occurred with the copying can't occur the way that it's implemented to the language. You won't things copied by the default copy constructor as virtual functions will not maintain the things that have been overwritten, and so on. So there are several changes and protections against bad calls and malformed statements. But the idea is exactly the same. Okay, so now if you understand this, you understand the idea. If you understand this coin dispenser, you understand the reasons, or at least one of the reasons why this is useful. And you also understand how this is a form, amounts to, at least in this case, a form of an abstraction layer, hiding unwanted detail from the person who is using an interface, an abstraction of an actual object instead of the actual object itself. Just like the bias hides from us the actual details of a keyboard and creates an abstraction layer so that we only think about keyboard objects and we don't care about what type it is, but everything, the code looks the same. Okay, so next time I'll get to the real type of virtual function, and we'll start using them. Okay, see you then.